And let's get to the quiz. So again, welcome Alexi and Susanna and Henry and Antonio and Estefani and Diego. Thanks for coming. And let us walk right into the quiz. Okay, so here's the quiz. And question 1, part A. If f of x, y, z is a differential function, derive the formula for del f, del phi, where phi is a standard with the standard spherical coordinate. Okay, so we need to find out del f over del phi. All right, well, the key here, it helps a lot, is to remember, how do you write x, y, and z in spherical coordinates? Do you remember the formulas? That was a big thing that happened a few weeks ago.
The r cos theta?
Yep, that's the start of it, but not r, the spherical, not cylindrical. So it's going to have a rho, not an r.
Yeah.
Okay, so we can say x is equal to rho cosine of theta, and then times, do you remember?
Sine of phi.
Yep, sine of phi. So this is just to start, because if you don't remember this, you pretty much have no chance. And then y. Y is very similar. What's the only difference with y?
It's a rho sine theta sine phi.
Yeah, so that cosine becomes a sine. And then z, do you remember what that z is? Has a rho. And then it's cosine, yeah, cosine of phi. All right, and what we want is del f del phi. I'm going to use d even though you shouldn't, just because it's just d for del. Just too much typing to do del a zillion times. So we want del f over del phi. And now it's time to use a chain rule. What does the chain rule say del f del phi is? I'll start you off. Del f over del x times what?
Del x over del phi.
Yep. Del x over del phi. And then we do plus. And then we do the same thing except for y instead of x, and then z instead of x. So I'm going to go just paste a few times, and then take those x's, make them y's. Take the x's, make them y's, and take the x's, make some z's. Any questions on that? Okay, then, now we're looking for the formula. So we get del f del x. What is del f del phi? If x is rho cosine theta sine phi, what is del f del phi? What is del x del phi? The idea is rho and cosine theta are constants when we want to do del f del phi.
Would be rho cosine theta cosine phi.
Yep, rho cosine theta cosine phi. So I'm going to copy, paste it in here and do an adjustment. And that sign becomes a cosine. And then similarly, del y del phi will be rho sine theta cosine phi. And then del z del phi will be, instead of rho cosine phi, it'll be negative rho sine phi. In fact, I think it's easier to just type this one. So the plus becomes a minus. And then we get rho times the sine of phi. Any questions on part A? Maybe write A. Okay, now part B. Part B is just using it. And now what we got is 2y minus 3xz. And we want del f del phi. So what I can do now is for B, I can just copy this in. And then now del f del x, just go over here. And del f del x is what? Yeah, negative 3z. So where I see a del f del x, I put a negative 3z. Del f del y is 2. So where I see a del f del y, I just put a 2. And del f del z is negative 3x. So where I see a del f del z, I put a negative 3x. Negative negative is positive, and I get 3x. And there's the answer. Any questions at all on using the chain rule, in this case, to find the derivative in spherical coordinates with respect to phi, where you're given a function in rectangular coordinates?
I have a
This stuff-
question.
Yeah.
So I think it was maybe just with like the x and y's where you couldn't leave them as x and y's, but like would you not have to plug in like the original rho, theta, and phi, like the square root of x squared? Do we not want it back in x, y, and z?
Yeah, really, the key is this is just a very general question, just mathematical. The problem I gave you is just a mathematical problem. And if all I give you is a mathematical problem, you can't know which is the better format.
Okay.
So to me, especially when you only have a 20-minute quiz, the better format is the one that takes the least amount of time.
Yeah, definitely, because I plugged it in and it took forever.
Yeah. Had I told you you had to plug it in, then you would have had to, but I didn't do that. Does that
Okay,
make sense?
thank you. Yeah.
Yeah. So the only time you want to plug in is when you're only given rho, theta, and phi, for example, and you're not given x, y, and z. Then plugging in sometimes is easier because then you have it in terms of rho, theta, and phi. But here we don't have anything, right? We don't have any numbers for anything. So if you happen to have x, y, and z, and you have rho, theta, phi, then the way I've got it is the best because it's the simplest. Okay, I wouldn't take off points to plug in, but again, you might run out of time if you do things like that. Okay, it's a good question. What's the best way? It's kind of like, what does it mean to simplify an expression? It all depends on what you want, right? Right? Is it better to have it factored or expanded? It all depends. So on this, whatever works for you, and my feeling is if it's less work, it works better. Okay, now let's look at question 2. Question 2 is let x squared z minus cosine yz plus 3xy equals 0. I'm going to find del z del y. Okay. By the way, if you tried to solve for z and then find the partial derivative, why would that be a complete nightmare? Right? Because technically that would work.
Would have too many steps.
Even worse than that. When you have a z, when you have a polynomial added to a trig, you can't without what's the complete sledgehammer that works for everything and is absolutely difficult.
Quadratic formula?
And here's the thing, you don't know it yet. And here's the bad news. That's the last 4 weeks of class.
I'm not looking forward to that at all.
Yeah, so we do have a very difficult last 4 weeks, and that's called power series. Okay. Yeah, bringing tissues, definitely. Some people like it, but most have a lot of trouble. Not a lot of trouble, but at least a lot of stress. Okay. Doesn't mean you can't get A's and stuff like that. People get just as many A's, but it looks weird and it can get a little scary and stuff. We're not. So the point is that you don't know at this point how to solve for Z. So you can only do this implicitly. There is no way for you to do this explicitly. And I will let you know, even after the end of this quarter, you will never want to do it explicitly, even when you know how to. Okay, just to let you know. It's what you do as a worst case scenario. So in this case, because we have to do it implicitly, who remembers the formula for dz, del z, del y? And I'm going to use d just because it's too hard to type a del. So dz over dy is equal to, do you remember the formula? It's pretty simple.
The negative of del f del y over negative, or yeah, the whole thing's negative. Del z, yeah, I'm messing this up. It's reciprocal. Del f over del y over del f del z.
Good. And again, I'm being a little lazy. I'm using d instead of del, just because. But I want to, let you know I'm doing that just because it's less typing. Okay. If I want it to be pretty and stuff, I'd use a math equation editor and all that. If you want to write del, you can also. Okay.
Yeah, I feel like it took way too long. Are we allowed to just say if we had d derivatives and dels, could we just use d and type out del?
So let me tell you, for the tests and for your quizzes, you can do that. For your presentation, you can't. Does that sound reasonable?
Yeah. Oh yeah. We don't have no time. Well, there's a time limit, but not really on the presentation. So we have time for that.
There's no time limit for preparing to make
Exactly.
a PowerPoint slide.
That's what I'm saying. I mean, well, there's a due date.
Yeah, there's
no
whatever, how many
time.
days you have
It's
until
a lot
now.
larger than a test. Yeah.
Yeah, it's like a few months of time limit, though, or a month of time limit. So I don't call that time limit. I call it a deadline, which is different than a time limit. Yeah. So yeah, on quizzes and tests, because we're online, then I'm letting you do D if you need to, but you do need to understand the difference between D and L. That you should know. So I could give you a true false question where, because I'm going to have it all right on the test. Does that make sense? Lecture is different, but when I write a test, it's like your presentation is that I have time to do it. So then you have to make sure that you understand the difference between del and D. Okay, but I'm not going to zap you for typing it wrong. Okay, so now we have negative. And again, the negative is the weirdest thing because the fractions seem like it shouldn't be a negative there, but it is. And we have negative, we need df or del f del y. So what is del f del y? F, by the way, is everything to the left of the equal sign. So if you have an x squared z and you want del f del y, what do you get for this term? Yeah, that's 0. So that goes away. Those are great. All right. And then you have a minus cosine yz. What's del f del y? So we got to use a chain rule. And z is our constant. The derivative of a constant times y is the constant, which is z. So it's a z that's outside, not the y. So it's going to be z times the sine of yz. And then plus, what's del f del y when you have the 3xy? 3x. Any questions on that piece? Okay, and then it's divided by del f del z. And what's del f del z when you have the x squared z? Yeah, that's just x squared, because x squared is now a constant. It's a constant times z. So just get x squared. Okay. And what is del f del z of negative the cosine of yz? Yeah, it's negative. Well, it's negative negative because we have already a negative, and the derivative of sine, derivative of cosine is negative sine, so you get negative negative is positive. And then the chain rule says you stick a y out, and you get positive y sine of yz. So I'm going to write times y sine of yz. Okay, and wait, it's not times, it's plus. And then what is a del over del z of the 3xy? Hope you find that easy. Yeah, that one's 0. So that's it, we're done. Any questions? Any questions on the quiz? Any questions? Okay, none of these are meant to be trick questions. You know, they're meant to be, you know, do you understand the basics and the, you know, the main formulas and how to use them? Any questions on question 1 or question 2?
Can you go back to question 2 so I can see the final thing? Thank you.
Yeah, there's not much work to show. Again, I like to show that piece, which is just the implicit way of finding the derivative of one variable with respect to the other. But otherwise, it's just doing it, you know, a little bit of chain rule.
I got it. Thank you.
Okay. Any other questions? Okay, let's get back to the webinar. And now I'm on Q&A time. Are there any questions about anything? Any questions? Okay, if there's no questions, I'm going to get into directional derivatives. As always, I have office hours after the lecture, so we can always, you know, ask more questions then too. But let's talk about directional derivatives. And I want to pop into a topo map. Okay, my favorite topo map, so sorry if I keep using the same beautiful desolation wilderness area. And if you are hanging out, maybe around here, next to this little pond over here, then we've already talked about the directional derivative in the direction of y and the directional derivative in the direction of x. So directional derivative in the direction of y is basically how steep is that first step you're going to have to take if you're going to go north. And the directional derivative with respect to x is how steep if you're going to go east. Any questions on that? Okay, but if there's a trail, so now let's walk along this beautiful trail. And maybe you're over here. And the problem is, or let's even do this one. I like this one better. So we're up here. Okay, this is the Bayview Trail. And if you haven't done the Bayview Trail, I strongly recommend it if you're in good shape. And you're going to take a step, but you're not going to, you wouldn't take a step north and you wouldn't take a step east. How come?
Of the line.
That's not what
in the way.
It's not where the trail goes. Trail doesn't head north and it doesn't head east. Does that make sense? And you want to understand how steep it is along the trail. Okay. And if you're heading, up the Bayview Trail, that means you're going up from like here to here. You're not going north. You're not going east. You're going southwest-ish. Does that make sense? And what you want to do is you want to find out not what it is east and what it is north, but what is it along the trail? How steep is it if you go in that direction? Okay. And if you look at most trails don't go north or east. They go whatever they go. Does that make sense? So you want to be able to understand how steep it is. And the word steep is the derivative. So you want to understand how steep it is, or what is the derivative as you walk along a trail or a path at which you're going in a direction that may not be north or east. It might be southwest, for example, or whatever direction you might happen to be going along that trail. Any questions on that idea? Any questions? Okay, well, how do we do that? That's the big question. Okay. My guess is that, if you had to do it, what you would do is, if you were there, is you would look at the trail. You would take a step. You kind of look to see what angle your foot's at. Does that make sense? And if it's at a high angle, then it's steep. If it's horizontal, then it's 0. If it's somewhat downwards, then it's steep downwards. It'll be negative slope. Does that make sense? But we need a mathematical way of doing this, where we have, instead of this picture, where we might have an equation, right? A function of 2 variables. And given that function 2 variables, how do you figure out how steep you're going in a given direction? Any questions on the goal? Any questions? Okay, so this is a biggie. Okay, this is a really, really important piece of multivariable calculus. And that is understanding the derivative in any direction you need to go in. So we're going to spend the next, almost hour talking about that. Okay, and we'll get into what's called the gradient in a bit. So let me go back and give you the big definition. And it's a bit messy. We'll do some examples. And it says the following. Let f of xy be differentiable. So as you might guess, if you can't take a derivative, good luck. We're not going to be able to figure out how steep something is if there is no such thing as a derivative. So we need to be differentiable. And let u be a unit vector. Now remember, unit vectors can be written in polar coordinates. And they're a little easier in polar coordinates than they are in regular rectangular coordinates. So why is it that rectangular coordinates would be hard to write down the general unit vector? Do you remember what the magnitude for a rectangular coordinates is? So if you have a vector in rectangular coordinates, do you remember how to find its magnitude? Yeah, you take the square root of x squared plus y squared, okay? Whereas if you're in polar coordinates, what is the magnitude? And the hint is it's very simple. Polar coordinates. So not 3-dimensional, we're still in 2. Yeah, it's just r. It's just r. Okay, that's like the point of polar coordinates, is that if what you're most interested in is the magnitude, you want to use polar coordinates because r is a lot easier than the square root of x squared plus y squared. So I'm gonna be in polar coordinates, and if I have a unit vector, that just means r is 1. Okay, and then x is r cosine theta, y is r sine theta, r is 1. So now you just get cosine theta comma sine theta. And that's our unit vector. I converted to polar coordinates and then I put it back into rectangular, and there we go, that's our unit vector. But theta is, again, that angle from the positive x-axis. So let's suppose you have a unit vector. Okay. And by the way, if you don't have a unit vector, you can always make it a unit vector by dividing by the magnitude. Then the directional derivative. Okay, again, this is a biggie today. The directional derivative of f in the direction of u, which is like I showed you on that map. If you take one step in the direction of u, which again might be southwest, then how steep are you going to have to take that first little step? And by definition, it is the first thing we write d sub u, capital D, which means directional derivative is how we read this. Sub u, the way we read that is in the direction of u. Because remember, when you have a unit vectors don't have magnitude, and the magnitude's 1, so it's not very interesting. But the direction is theta, and that's the one thing that gives you the unit vector is the direction. So the directional derivative in the direction of u of the function f evaluated at the point AB is the limit as h goes to 0. And now we're basically taking what you're used to in terms of the limit definition of the derivative, right? Remember, the standard limit definition just for one variable was the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, there's a lot like that, right? Here our x is a comma b, and then our we're not adding h anymore. Now we're writing h times the unit vector. So the direction of the unit vector with magnitude h. So that is a plus h cosine theta, comma b plus h sine theta, minus kind of like f of x, but f of ab, divided by h. So here is our definition of the directional derivative. It's a lot easier to just look at a map and imagine yourself walking than it is to write this down, but you are responsible for it. So I want to stop and ask, are there any questions about this definition? Okay. Why does this match up, by the way, with the partial derivative? So why does this give you the definition of both partial derivatives all in one? Anyone see it? Give you a moment. So why is the definition of partial derivative part of this, like immediate from it? Of course, you got to remember the definition of partial derivative, the limit definition. I don't see y'all jumping in, so maybe I'll talk about it. Okay, so for example, the partial derivative with respect to x, that's a definition, that's the directional derivative in the direction of the vector 1, 0. Because 1, 0 is in that x direction, right? Because 1, 0 means you move along the x-axis 1 and don't touch y. So if we're looking at 1, 0, that means theta is 0. That's another way of looking at it. So in the x direction, that means that our angle theta is 0 because the positive x-axis has an angle 0. And if your angle is 0, then notice cosine of 0 is 1, sine of 0 is 0, and you get f of a plus h times 1, which is just f of a plus h, comma b plus, and then 0, or just b, minus f of ab over h. And that was the definition of the directional derivative in the direction of x. Okay. Similarly with y, the y-axis, it has angle pi over 2. Cosine pi over 2 is 0. Sine pi over 2 is 1. So that means that in this case, this h cosine 0 goes away. The h cosine theta goes away. the h sine theta becomes h, and that gives you the definition of the partial derivative with respect to y. So this basically has all of the definitions in one shot. Any questions on this so far? Okay, let's do an example. So how about f of xy equal x minus 2xy. Find the directional derivative in the direction of the vector 1/2 comma square root of 3/2. Of f evaluated at the point 2, 1. Let's go 2, 3. So what do we do? And the idea is we plug in. So I'm just going to pop this in. It shouldn't be red because it's not that important. But it doesn't let me. So let's do it this way. There we go. And let's look at this. So now we have a plus h cosine theta. Okay. So that cosine theta, that's just the 1/2. And then a, by the way, was 2. B was 3. And then h sine theta was root 3/2. Minus f of 2, 3. And let's just calculate f of 2, 3. So if x is 2 and y is 3, you get 2 minus 2 times 2 times 3. 2 times 2 times 3 is 12. 2 minus 12 is negative 10. So that means we get a plus 10. Any questions on that? Did I get that right? Yeah. Any questions so far? All right, what I like to do, so I'll do it again, is copy paste. And let's grab what this f is. So we have f of this 2 plus h/2, 3 plus h root 3/2. Well, f now is x minus 2xy. So x is 2 plus h/2. And then we're supposed to do minus, and then we're supposed to do 2xy. So we have 2, let's write this out, 2 times 2 plus h/2 times, and then the y was 3 plus h root 3/2. Like so. Any questions on that? Okay, so now what's the next step? hint is it's easy and hard. Yeah, we just simplify. So I'm just going to look at the constant term. Notice you get 2 minus 12 plus 10. So the constant goes away. Okay. And then notice also this h over 2 times h root 3 over 2 over h gives you an h, and the limit as h goes to 0 is just 0. Okay. So that's not a problem. Really, all that matters is the first degree term in h. So that's all I have to focus on. So I can change the numerator to, well, we're going to have an h over 2. Let's just write it. And then we're going to have a minus. And then we're going to have an h over 2 times 6h over 2. Okay, or that's just h over 3. So minus h over 3. And then I'm going to write plus O of h squared. Who remembers what O of h squared is? You get into computer science a lot. It's a big deal in computer science, but it also happens occasionally in math. Anyone know? Okay, it means it has a characteristic of the h squared function. Okay, so it's going to be, if you divide by h squared and take a limit, you end up getting a constant. And in particular, if you divide by h and take a limit, you get 0. So it goes away. And all you get now is we can cancel the h's, and we just get a half minus, was that h over 3? Sorry about that, I think. Let me double check. I think I made a mistake there. See, that's the problem. You should be checking my work here. So we had 2 h over 2 times 3. I have one more term. So 2 times h over 2 times 3. So that's h times 3, or 3h. And then the last one, we have an h root 3 over 2. I forgot that piece. Times 2 times 2, which is 2 root 3h, or 2h, h times 2 root 3. And that is a minus h times 2 square root of 3. And the idea when h goes to 0 now, the O of h squared goes away, all the h's go away, and you just get a half minus a third, which is a sixth, and then minus 2 root 3. If I did everything in my head right. Okay, notice it's a number, and that's it. I forgot the over. All right, are you convinced that you don't want to do this?
Absolutely.
That was part of why I did it. And part of why I didn't keep asking you, all right, what's the next step? What's the next step? What's the next step? For getting these, okay? And I'm not even 100% sure if I didn't make some kind of algebra mistake or something, but okay. So my guess is that you're convinced. If not, then you're, you have an interesting personality. I'll just put it that way. Okay, it's my job. I have to do it. So that brings us to the big topic, and that's called the gradient. So here's a big definition, huge. Okay, this, and it's the following. Let f of x, y be differentiable. Okay, and you're used to that. If you don't have differentiable and you want to do calculus, good luck. Do you agree? Good luck taking a derivative if it's not differentiable. So we're gonna let f of x, y be differentiable. In the real world, not everything, but a lot of things are differentiable. Okay, there are, in the real world, there are cases where you get non-differential functions. The main examples are in electricity. Where do non-differential functions happen in electricity? Right, so electrical engineering. Yeah, in circuits. So in circuit analysis, and you all know this because you do this every day, and that is turn on the light. And when you turn on the light, you are doing a sudden, change. It goes from off to on, and then you turn it back on, off, and it goes from on to off. It's a sudden change, and that's just the way it is. Okay. Others, and you know this from hiking, for example, and that's cliffs. You could have a cliff, and then you get a non-differential function in terms of elevation. In hardcore physics, there's black holes. That gives you all kinds of non-differentiability. But most things are differentiable. So we're in good shape. So if f is differentiable, then the gradient, very important, of f is defined by. It's so important, there's actually two different notations for it. Okay, which you're used to with calculus because there's kind of like Newton's and Leibniz, but this isn't even Newton and Leibniz. I don't even know who came up with these. But one is grad f. Okay, and the other, anyone know how to read this symbol? And don't say triangle, by the way. Okay, one way to read it is grad. Okay, it's a capital delta, it turns out. It's a capital del, and it's del f, but it's grad, it's a gradient of f. The hard part about this symbol is typing it. It is tough, even in Google Docs. It was hard for me to get this down. And here's the big definition. It is the vector at which the first component of the vector is a partial derivative of f with respect to x, and the second component of the vector is a partial derivative with respect to y. So what it does is it puts both partial derivatives together in one package as a vector. Any questions on this big definition? Okay, and as I mentioned, this is a biggie. Okay, it's kind of like, what was the most important definition in first quarter calc? What was the definition of? What was it called? One word?
Derivative.
Derivative. Okay, and I think you agree derivatives were really important in first quarter calc. Okay, this is the derivative for functions of multiple variables. Okay, this is the derivative. So this is as important as the derivative in first quarter calc. Gradient of f is the biggie. So you need to know it. Okay, and you need to not just know it so that you can refresh yourself and have to think about it and then remember it. No, you need to have this down. So if anyone says gradient, you don't have to think. You just have this down. The gradient of f, or del f, is equal to fx comma fy. Okay. Any questions on this? Okay, it's not a very hard definition, but it is really important. Okay. Yeah. So look at that. We have someone who actually used it already before I even talked about it, because it's that important. All right, so now that we know it, let me just do some. Let's suppose I just make them up. Take a gradient of anything that is a decent function. So let's suppose f of x comma y is equal to, how about 3x minus y of x. So find, let me write down example. Find the gradient of f. All right, I'm going to give you a moment or two. And I want you to do it because I don't think I need to do an example. I think I can have you do an example because the definition uses the things that you've already learned. So it's not like there's some new trick you have to learn. And when you've got it, put it in the chat box. And let's see if you can find the gradient of f. And hopefully you can all get it. We have one person put it in. Let's see if we get some with the same or different. We'll see. Okay. All right, good. We're seeing the same. So let me do it, even though most of you hopefully are getting it anyway. So, and I'm gonna do it in another notation just to remind you that there's different notations. So first I find the derivative with respect to x. Derivative of 3x with respect to x, that is 3. And the derivative of y over x with respect to x, y is a constant. So that's a constant times x to the negative 1. And the derivative of a constant times x to the negative 1 is negative the constant x to the negative 2. Negative, negative cancel. You get plus. And you can write as negative 2. I'm gonna write, so we're gonna have the constant, which is y, times x to the negative 2. And you could write y over x squared. That's all up to you. And that's the derivative with respect to x. And I'm going to do it in ij notation just so you can get used to it. Sometimes I like to kind of show you both. So I plus, and now we take the derivative of f with respect to y. So the derivative of f with respect to y, if we have 3x, that's just 0. There's no y. And if you have y over x, that's the same thing as saying y times 1 over x. 1 over x is a constant when you're talking about with respect to y. And that's just a constant times y, so it's just a constant, which is just 1 over x, and it's a minus. So it's a minus 1 over x, j. So I want to mention that there's kind of two main ways of writing vectors. The first is in the pointy bracket notation, and the other is the ij notation. Okay, and I'd ask you, which is the better way, but that'd be a trick question. It all depends on what works, what you're doing and what works for you. If you want to extend it to 10 variables, ij never works. Just let you know that. You have to use pointy brackets. But in 2 variables, a lot of people use the ij notation. Any questions on this example? Not too bad? Okay, so again, we have this definition of the gradient, but a bigger question you might have is, I advertise this as the most important thing in all of vector calculus, but you look at it and it doesn't look very important, does it? It's just a couple derivatives with a comma in between. So now it's time to talk about why is it the gradient's important. And today we're going to do some of it. The bigger importance actually comes later, okay? Which I think is actually Friday, but I'm not sure. Might be Monday. So here's properties of some of the properties of the gradient. And there's more, but these are the ones from this section. Okay, so the first one, if the gradient of f is equal to, I think I want to change this, the 0 vector, then the directional derivative in the direction of u of f of AB is equal to 0 for all u. So if the gradient is the 0 vector, then the directional derivative is always 0. Any questions on that? Okay. So this turns out to have a really, really important application, which I'm going to do next time. Okay, the next, if the directional derivative, I'm sorry, if the gradient of f at AB is not the 0 vector, then the gradient of f is the direction that maximizes the directional derivative in the direction of u of f of AB. Okay, and the maximum value of directional derivative in u and f of AB is the magnitude of the gradient of f. Okay, this is huge. Okay, this is really important. Why do we care? Can you think of some applications on why you care about the fact that the gradient is the direction? When the gradient is non-zero, the gradient of f is the direction that maximizes the directional derivative. Why do we, can you think of some applications on that? And there's many really important applications, not little minor things. Can you think of some applications? There are in most STEM fields, maybe all STEM fields have this as an application, as a big application. Yeah, so electric fields. So what that says is if you want to see where the maximal changes in electrical field strength, then you take the gradient of that electrical field function, and that gradient at that point will be the direction of maximal electric flow. Okay, where else will you see it?
Water, like the flow
Okay.
rate of water.
Exactly. So if you have water, okay, flowing wherever, then it's where it flows. Okay, so that's kind of, we can go back to the map. Okay, so if we got this map and you're dropping water from here to some point, and you want to find out where it's going to flow, it's going to flow in the direction of the gradient. And that will be the flow, and that's where the creek will lie. Okay, we'll end up with that because water always wants to flow in the direction of maximal steepness. Okay, where else does it happen? It happens in many, many applications. Anyone know where it happens in a biggie in computer science? You may not know this one, but it's a huge one in computer science. It's where the right now where all the big research is happening, you know, and all the main work in computer science is all happening here.
Cybersecurity.
That's some research. It's not the biggest research, actually. Okay, AI. So what you have is then you have a function, typically not of 2 variables, but we're going to see that it doesn't matter if you have 10 variables or 30 variables, it still all works. Then what you're going to want to do is you want to see with AI, how do you get to that optimal point? Okay. And the way you get to the optimal point is called gradient descent or gradient ascent, which means you find the function at which it talks about. So if you want to maximize the efficiency of your robot as it's moving, then, and it's based on many variables, then what you do is you move it to, or you go in those variable directions along the gradient, and that is most likely to maximize efficiency. It's pretty complex. I'll let you know that. That's why you make lots of money if you decide to go into it. But that's a biggie is called gradient descent and gradient ascent in AI. It's a biggie. Another biggie in chemistry. Where does it happen in chemistry?
Would it just be concentration gradients?
Concentration, it could be, but what's the function in this case?
I would imagine equilibrium.
Yeah,
Like
and where is
reaction
equilibrium?
kinetics.
Right, so to get to equilibrium, then it's going to have to do some kind of chemical reactions, and it turns out it's going to make it happen, and it's going to go along the gradient. Okay, it's going to do a gradient path. Okay, where does it happen in biology? Okay, Darwinism. Okay, Darwinism. Okay, now you're talking about genetics, and how are species going to change? Species are going to change along the gradient path of maximal progeny. Okay, so it's everywhere. So I want to let you know this is the most important topic. It is in every field of STEM. So just let you know that whatever you're in, I can give you examples. But I want to go on because we still have a little more to do. But again, it's all about gradients. Okay, the next one, number three. Number three is obvious, I hope, that if the gradient is the direction where you're going to maximize going up, and instead you want to maximize going down, what do? You turn around. Do y'all agree? So if northwest is the direction at which you're going to go the steepest upwards, well, guess what? Southeast will be the steepest downwards. Do y'all agree? So number three says if the gradient is non-zero, then negative the gradient of f of AB is the direction that minimizes the directional derivative of f of all possible directions. Okay, and that minimal value is negative the magnitude of the gradient. Okay, that should be obvious. Do you agree that's obvious? That the opposite direction will be going down the most? Okay, so those are important properties. What I'm not going to do is spend all the time proving them, because then we can't do examples and all that kind of stuff. This isn't just a proofs class. This is learning how to do calculus mostly. Okay, but we do have a big theorem. Okay, and actually we can have this theorem, and it says if the gradient is not zero, then the gradient is orthogonal to the level curve of z equals f of xy at the point AB. Okay, actually this should be parentheses. So again, if you take that picture, then and those of you who are used to looking at topo maps and working with them, you probably already know this, that if you want to, if you're over here somewhere and you want to say what's the steepest possible climb direction, then how do you know what the steepest possible direction is to climb it from the point that we're looking at? From looking at this contour diagram or topo map. So what's the steepest? Okay, so I'm at a point. So we're not gonna, not where is the steepest on this whole map, but if you're standing at this point in Desolation Wilderness and you're looking at your map and you want to take one step that is the very steepest uphill, how do you know what direction to go? That's the question. Anyone know? Maybe I'm a hiker, so maybe I'm just assuming you guys have done this stuff too, but maybe not. Okay. The direction to go to be the very steepest is orthogonal or perpendicular to the topo line. So I'm going to go that way. Whoa, that way. And that will get me in the steepest direction. If you go along the topo line, then you're not going up or down at all. If you go orthogonal or perpendicular to the topo line, then you're going to go the very steepest, up or down, depending on which direction. Does that make sense? Any questions on that?
I sort of have a question. I think I get what you're saying, but so we're talking about like infinitesimally small, right? Like it's
Exactly. When I say one step, I mean a tiny, infinitesimally small step. Okay. You're not going to take a step all the way to Granite Lake. You're going to take a tiny step. And that tiny little step is going to be in the direction of the gradient if you want that step to be as steep as possible. Okay. Or another way is if you drop water at that spot, what direction is it going to flow at that point? And it will flow orthogonal to the topo line. Any questions on that? So that is a very important theorem. And it's immediate from the property. Okay, but again, I decided today's not going to be a big Proust day. Okay, and then for higher dimensions, du, the directional derivative in the direction of u of f, and the gradient of f extend naturally. So my guess is I could give you a problem without showing you how to do it, and you could do it. Let's see if I'm right. So let's suppose that f of x comma y comma z. Can we see the last one for a second? The theorem, you mean? So there's a theorem. It just says that the gradient is always orthogonal to the level curve. Okay, as long as the gradient is not zero. That's what that says. Is that okay? Okay, so if f of x, y, z is equal to x, y squared, z minus 2yz plus 3x, let's first find the directional derivative in the direction of, how about yeah, there's no way to have nice things. So you got to have square root. Unit vectors are always ugly. Square root of 2 over 2, comma, square root of 2 over 2. Hopefully you agree that's the unit vector of f at the point 2, comma 1, comma 0. So how do we do that? So again, I haven't officially defined it when it's in 3 variables instead of 2. Oh, you know what? That's a mistake. Let's do this again. Oh, it gets even worse. How about a third 2/3. And does this work? 2/3. How about -2/3? Yeah, actually, it's nicer. Okay. Notice that's a unit vector. 1 + 4 + 4 is 9, 9/9, and you get 1. Okay. So how do we find this directional derivative? In fact, I don't even need to call it A. I'm just going to do it. So what's the easy way of finding a directional derivative? Because the last thing I want to do is that limit stuff.
Derivatives.
Okay. What I'm going to do is I'm going to take the partial derivatives. And let's do that. I'm going to take the gradient. And I'll use grad of f is equal to. So what's the first component of the gradient of f? Yeah, it's s sub x, but it's y squared z plus 3. Stop me if you're not following how I got that. I took the partial with respect to x of f. And what's the second component? Yep, 2xyz minus 2z. And what's the third component? Hopefully you can get it. Partial with respect to z is going to be xy squared. And then we're going to have a minus 2z. So that's a minus 2yz becomes a minus 2y. Any questions so far? Okay, now I want the gradient of f at the point 2, 1, 0. So now I just plug in. So z is 0. So y squared z plus 3 is just 3. And then 2xyz minus 2z is 0. And then xy squared is going to be 2 minus 2y is another 0. Any questions on that? Okay, now comes the big deal. And that is, how do you find the partial derivative? How do you find the gradient? I mean, how do you find the directional derivative? So here's a big, I don't think I've mentioned it yet, but I'm going to now. I don't think we have that as a theorem yet. I'm going to do it in 3 dimensions, and then you can do it in however many you want. The theorem is, let's see. The directional derivative in the direction of u of f is equal to the gradient of f dotted with u. And that is an absolutely beautiful theorem. Because now this is really easy to find the directional derivative once we found the gradient. I bet you can all do it in your head. What is the directional derivative in the direction of 1/3, 2/3, negative 2/3 of f at 2, 1, 0, given the fact that I've just found the gradient to be 3, 0, 0? Okay, it's a dot product. Dot products are numbers, not vectors, so be careful. So we're going to take the gradient of f, which is 3, 0, 0, and we're going to dot that with the 1/3, 2/3, negative 2/3. Yep. So 3 times 1/3 is 1, plus 0 plus 0 is 1. Any questions? Any questions on this main application? Okay, so this is a big application of the gradient. It allows you to find the directional derivative in a whole lot easier way. If you didn't have this theorem, what would we have to have done?
Is it cross product?
No, not cross product. Let me remind you what we did last time. I mean, last time as in earlier today. Remember this?
That would have been a horrible experience.
Yeah, what you would have needed was a lot of Kleenex. Because, boy, it would have been miserable. But with the gradient, actually, it's quite easy. Do you all agree? With the gradient, you just take the gradient, you plug in, you take the dot product with that vector, and that's it, you're done. By the way, if the vector is not a unit vector, and you want to find the directional derivative in the direction of something that's not a unit vector, what you do is you just make it a unit vector. Divide by the magnitude, and then do what you have to do. Okay, that's just a note. Okay, now comes the next big theorem. Okay. And this is the one this is why the whole tangent plane thing, I wish that came after this section, because you had to get tortured with tangent planes. And now we have a much better way of remembering the tangent plane. And here's how it goes. Okay, let f of x, y, z equals 0 define a smooth surface. Then the normal vector to the tangent plane for f of x, y, z equals 0 at ABC is the gradient of f at ABC. Isn't that a beautiful, easy to state theorem? So as I mentioned, the gradient is everywhere in multivariable calculus. So an example, find the equation of the tangent plane to the surface f of x comma y comma z equals 3x minus yz equals 0 at the point one comma 3 comma 1. So how do you do that? To find the equation of a tangent plane, what main vector do we need to find? Yeah, the normal vector. But guess what? The normal vector by the theorem is the gradient. Isn't that beautiful? So we just take the gradient. So the gradient of f, what's the gradient of f? It's not supposed to be hard. I didn't give you a hard one. What's the x component of the gradient of f? It's going to be 3. Okay. The y component of the gradient of f will be negative z, but there's a z component too. And the z component of the negative of the gradient of f will be negative y. And the gradient of f at the point 1, 3, 1. Now just plug in. Equals 3, comma, negative 1, comma, negative 3. Any questions on that so far? And the big theorem says this is n, the normal vector. So now the normal vector is always orthogonal to any vector on the plane. So now I can write down the equation, and I could say 3, negative 1, negative 3 dotted with.
Larry, how'd you get 3, negative 1, negative 3?
So I plugged in. So the first coordinate is 3, no matter what x, y, and z are. That's just a constant, right? So that stayed 3. And then it said negative z. Z is 1. So negative z is negative 1. And then it says
Okay, sorry. Yeah,
negative y, and y is 3. So negative y is negative 3. That makes sense?
yes, thank you.
Yes, I plugged in. Yeah, nothing fancy, I promise. Okay.
Actually, Larry, I have a question. If there was no z, if this is only like x and y, would z be negative 1? Or would that not really be a good application?
Okay, so if it'd be kind of boring if there was no z here, then the third component of the gradient would be 0.
Okay.
Because the derivative of something, if that variable is not even there, then it's just a constant and the derivative is just 0. Does that make sense?
Yeah, no, I mean, I think I'm just a little not confused, but I was thinking the other day when you said that if there is no z, it's negative 1, but then there's also
that was
a 0 too, so I get that.
Yeah, right. But now we're in a different situation. Now we're in a
Right.
situation of what's called an implicitly defined surface. So it's f of x, y, z equals 0. Okay. If you have z as a function of x and y, you can always subtract the z and then make it a function of x, y, and z. So this theorem works for anything. Okay.
Yep.
And that's how I always remembered it, in fact. Okay, then we're going to dot it. So we take the gradient and we're going to dot it with a vector in the plane. And that's going to be x minus 1, comma, y minus 3, comma, z minus 1. And that's equal to 0. Okay, and then the rest is kind of busy work. So we get 3, x minus 1, and then minus y minus 3, and then minus 3, z minus 1 equals 0. Okay, and that is the equation of the tangent plane. If you wanted to get z as a function of x and y, you can always do algebra. Okay, multiply through and solve. Okay, but this is definitely an equation of the tangent plane. Isn't that easy? And easy to remember? Just take the gradient, dot it with the displacement vector, get 0, and that's the equation, period. Okay, we are out of time. So I'm going to stop the share and stop the recording.